What we want to do is to generalize the behavior of equality of numbers. So what I'm referring to is if, for instance, x is a real number, well, we can always say that it is equal to itself. If we have x is equal to y, then this necessarily means that y is equal to x. And finally, if we have x is equal to y and y is equal to z, necessarily we can say that x is equal to z. So we want to generalize this right here so that it can work on any set. We're going to start with a relation tilde on a set S is said to be an equivalence relation. An equivalence relation on S if it is, and we're going to have three criteria here. The first one being that it is reflexive, and we'll denote that by R in parentheses. And what this means is for all elements x that is in S, we have that x is related to itself. This means that equality is reflexive. Our second criteria is going to be that it is symmetric. Symmetric, and we'll denote that by S. That is for all elements x and y that are in S, such that x is related to y, we have that y is related to x. Okay, so equality is also symmetric. And the last one is that it is transitive. Transitive, and that is T. Now, for all x, y, and z that are in S, such that x is related to y and y is related to z, we have that x is related to z. Equality is also transitive. What about, let's go over some examples. Obviously, we've gone over equality. We can also talk about similarity of triangles. What this refers to is, remember in high school, we've learned that two triangles are similar if they both have the same angles. Okay, and it is reflexive because a triangle has the same angles as itself. It is symmetric because if we have a triangle A that has the same angles as the triangle B, well, the triangle B has the same angles as triangle A. And similarly for transitivity, if we have a third triangle C, well, if A has the same angles as the triangle B and B has the same angles as the triangle C, well, A has the same angles as the triangle C. That was a tongue twister. Oh my God. I will never say that again, I swear. Okay, so we can also say that parallelism is an equivalence relation. Now, the way we're going to define parallelism is that if we have a line A that is equal to A times x plus B, and another line 2, let me rewrite that, a line 2 that it is C times x plus D, then we're going to say that L1 is parallel to L2 if and only if they have the same slope. So A is equal to C. Now, this is an interesting case because it is an equivalence relation because we've defined it using equality. Okay, this means that it is the proof is going to be relatively easy, okay? All my proof is going to consist of is using equality. Because A is equal to A, we necessarily have L1 is parallel to itself. Now, if I have for symmetry, if L1 is parallel to L2, this necessarily means that A is equal to C, right? Because we have this condition if and only if A is equal to C, but we know that equality is an equivalence relation, which means it is symmetric, which means that C is equal to A. Therefore, we can say that L2 is parallel to L1. And we're going to do the same thing for transitivity. Let's say I have a third line L3, which is E times X plus F. Now, if L1 is parallel to L2, and L2 is parallel to L3, what I can say is that A is going to be equal to C, and C is going to be equal to E. Let me just get that down right here. Now, equality is transitive, which means that A is equal to E, and this allows me to conclude that L1 is parallel to L3. So it is reflexive, symmetric, and transitive. Parallelism is an equivalence relation. Now, what about perpendicularity? Well, it turns out that it is not even reflexive, so it cannot be an equivalence relation. Because if we have a line L1 right here, well, L1 cannot be, it cannot form a right angle with itself. Actually, we could define perpendicularity as L1 is perpendicular to L2 if and only if the product of A and C is equal to -1. So that's one way to define it. For symmetry, well, obviously, it's going to be, what am I doing here? I'm drawing axes. If L1 is perpendicular to L2, obviously L2 is going to be perpendicular to L1. And for transitivity, if L1 is perpendicular to L2 here, and L2 is perpendicular to L3. Well, actually, it's impossible for L1 to be perpendicular to L3. Actually, it's going to be parallel. So we have right angles right here. So it is not transitive, it is not symmetric, it is not reflexive, but it is symmetric. So let's go over and overview. Remember that a relation on a set S is said to be an equivalence relation on a set S if it is reflexive, which means that for all, the quantifier for all x that is in S, we have that x is related to itself. It is symmetric. That means that for all x and y that are in S such that x is related to y, then we have y is related to x. And it is transitive, which means that for all x, y, and z that are in S, x is related to y, such that x is related to y and y is related to z. Then we have that x is related to z. Okay, so we took the familiar notion of equality, the familiar behavior of equality, and we generalized it to so that it can work on an arbitrary set.